Every time you ask an AI to book a flight or, check the weather or even deploy code, the AI itself is doing absolutely nothing.
Right. Nothing at all.
Like, it has no internet connection, it has no hands, it is entirely paralyzed. And today, we are basically dismantling this whole illusion of the intelligent agent, I guess you'd call it,
Yeah, that's a good way to put it.
because we want to show you the actual plumbing that runs the modern world. I mean, you are constantly being hit with this absolute avalanche of buzzwords, right? LLMs, RAG, context windows, function calling, MCP, agents,
It's
skills.
exhausting. It really is.
It is. And if you're operating in the tech space right now, just trying to build with these tools, or even just like trying to understand the architecture, the sheer volume of marketing jargon is completely overwhelming.
Oh, totally. The industry, it really relies heavily on creating this sense of mystique.
Yeah.
It actually benefits companies to take like standard software engineering patterns and package them up as these revolutionary new forms of intelligence.
Right, like it's magic.
Exactly.
Yeah.
But when you look at the actual source code, the reality is, well, it's far more mechanistic. It's rigid.
Which is exactly what we're getting into in this deep dive. Because what if I told you that beneath all the glossy product launches and the, academic-sounding acronyms, every single one of those concepts is fundamentally the exact same thing?
And that's really the core of what we're looking at today. We've got this incredible breakdown from an AI operator named Harrison. He actually builds these systems from the ground up.
And his research is fascinating.
It really is. He essentially deconstructs the entire AI stack, just strips away all the marketing to reveal this very deterministic set of pipelines.
Okay, let's unpack this. Because the central thesis of his breakdown, and this is the phrase that is going to serve as our anchor for this entire deep dive, is just 4 simple words: LLM talks, program walks.
I love that phrase. It really captures the whole dynamic perfectly.
It's so good. LLM talks, program walks. And by the end of the session, you are going to have a purely mechanical mental model of how AI actually operates.
Yeah, so you'll be able to look at literally any new framework that drops, ignore the hype completely, and just instantly map it to standard software architecture.
Exactly. So let's build this architecture from the absolute bedrock, right? Layer 1,
Hmm.
the illusion of intelligence.
Like the atoms of AI.
Because we all know that autoregressive models are just predicting the next token. Like if I type the capital of France's, the model just says Paris.
Yeah, they aren't brains. They're just probability engines.
But what Harrison's research highlights is how that stateless token generation actually interfaces with a real stateful environment. And to understand that interface, we have to look at the raw input and output format. Because the model itself, it doesn't actually process text, does it?
No, not at all.
Yeah.
It processes math. High-dimensional matrices, pure numbers.
Right.
And so the very first bottleneck in the whole pipeline is the tokenizer. And it's really easy to fall into the trap of thinking a token maps cleanly to a word.
I think everyone assumes that at first, like one word equals one token.
Exactly. But the mechanism is much stranger. It uses these algorithms, like byte pair encoding, or BPE.
BPE.
Right.
Okay.
And the tokenizer, it basically scans a massive data set and finds statistical groupings of characters. So a word like helpful isn't the single concept to the model.
It splits it up.
Yeah, it's the vector representation of help combined with the vector representation of full.
And my favorite example from the source is the word unbelievable, because that actually splits into 3 tokens, right? It's un and then believe and then able.
Exactly. And what's fascinating here is that the tokenization process is completely, utterly ignorant of human linguistics.
It doesn't care about grammar.
No, it doesn't know what a noun or a verb is. It's purely an exercise in data compression. The tokenizer just compresses a string of text into an array of integers, and those integers point to specific vectors in a high-dimensional space.
Just coordinates, basically.
Right, so the entire multi-billion parameter neural network is simply running floating point math to calculate the trajectory of those vectors. And then it probabilistically selects the integer that, mathematically speaking, belongs next in the sequence.
And then the tokenizer just decompresses that integer back into a text fragment so we can read it.
Exactly.
It's like an actor phonetically reading lines in a language they don't actually speak.
That is a perfect analogy.
Like they know the sounds go together and they can mimic the cadence perfectly, but there is zero inherent comprehension.
None. Just pure pattern matching on an atomic level. Tokens are the absolute atoms of the AI world. Everything in, everything out is just tokens.
Okay, but this brings us to layer 2. Because this is the logical pushback, right? If it's just a math function predicting the next atom of text, and we're saying it has zero
It
memory,
does. Zero memory.
right, then how on earth does it remember my name from a message I sent like 10 minutes ago?
Yeah, that's the illusion of memory. And it's a really powerful illusion.
Because it feels like a continuous conversation.
It does. But the statelessness is a non-negotiable property of the neural network architecture. During inference, the weights of the model are frozen.
So nothing I type actually changes the model itself.
Exactly. Nothing you type alters those neural pathways. Therefore, the entire burden of memory has to be offloaded to the surrounding software. And this is where we introduce the concept of the context window.
Ah, the famous context window.
Right. Since the model cannot remember the past, the software wrapping the model, the program, must constantly resubmit the entire conversation history as part of the present input. Every single time.
Wait. So it literally rereads our entire chat history from scratch for every single reply.
Every single time. Input in, output out.
That sounds absolutely exhausting.
It's computationally very expensive. Think of the context window like a desk. Harrison uses this great analogy. You're sitting at a desk, and you can only work with the documents that are physically sitting in front of you.
Right.
The desk has a size limit. Today's leading models, they have a window of about 1 million tokens.
Which is massive, actually. That's roughly, what, 750,000 words?
Yeah, it's about the entire 7-book Harry Potter series.
So the desk is huge now.
The desk is huge. But here's the inefficiency. Even with a huge desk, dumping a 1,000-page manual onto it every time you want to ask a single question is a terrible idea.
Right, because aren't we just nuking our API budget doing that? And introducing massive latency?
Exactly. The computational overhead of the attention mechanism inside the transformer, it scales quadratically with the length of the input.
Meaning it gets exponentially slower and more expensive the more stuff you put on the desk.
Yes. So while you technically can put the whole manual on the desk, doing so degrades performance. And this architectural flaw is what necessitated the development of RAG-AI.
Retrieval augmented generation.
Right.
Let's actually trace the mechanism of RAG-AI, because this term gets thrown around constantly. People talk about it like it's a magic bullet for memory, but it's really just a dynamic routing system, right?
That's exactly what it is. It's a filing cabinet next to the desk.
Right. So instead of dumping that 1,000-page technical manual onto the desk every single time, RA relies on vector databases. You take that massive manual, you chunk it into smaller paragraphs, and you run those paragraphs through an embedding model.
Right, and the embedding model converts the semantic meaning of each chunk into a dense vector.
A coordinate.
Yes, a coordinate in a multidimensional space.
Yeah.
And you store all those coordinates in a database.
Like Pinetone or Milvus or whatever.
Exactly.
Yeah.
So that pre-processing step is critical. You're building an index. Then, when you eventually ask a question, the software does not send your question straight to the LLM.
It stops it.
Right. First, it sends the question to the embedding model to get its vector coordinate. Then it runs a similarity search in the vector database to find the text chunks that exist closest to the question's coordinate.
It's pure geometry at that point.
Pure geometry.
It just calculates the distance between the question and the stored paragraphs, grabs like the top 5 closest matches, pulls the actual text of those chunks, and injects only those specific paragraphs onto the desk, into the context window.
And the efficiency gains there are massive. You bypass that quadratic scaling problem because you are strictly limiting the token count. You're giving the stateless text predictor the exact context it needs without flooding the engine.
So the API costs drop, latency stays low.
Exactly.
Okay, so now we have a text predictor with a pile of highly relevant context sitting on its desk. Layer 3, how do we actually tell it what its job is?
This is where we demystify prompts.
Right, prompt engineering, the dark art.
The dark art that really isn't so dark. A prompt is simply what you say to the LLM. But structurally, you're passing distinct variables to an API. You have the user prompt and you have the system prompt.
And they do entirely different things.
Completely different. The system prompt is the hidden set of rules set by the developer. It dictates who the AI is and its constraints. Like, you are a senior Python engineer, keep answers concise, never use markdown formatting.
So it's like the director's notes given to an actor before the play even starts.
I like that, yes.
And then the user prompt is what I actually type into the chat box. Write me a sorting algorithm. It's the script the actor is reacting to in the moment.
Right. The system prompt sets the physics of the environment, and the user prompt is just a localized command executing within those physics.
Okay, so it can predict words, it can read its history from the desk, and it can follow a persona based on the system prompt, but we still just have text on a screen.
Just text.
Which brings us to layer 4, the core loop, function calling. Because how does it actually do things? If I ask it to check the weather, how does it do that?
And this is the most critical part of the entire deep dive. If we connect this to the bigger picture, this is the dividing line of modern AI.
Here's where it gets really interesting, because we have to reiterate this hard truth. An LLM can only output text.
It cannot browse the internet.
No.
It cannot call an API. It cannot read files. It is air-gapped.
It is entirely paralyzed. So let's break down the weather in Tokyo example from Harrison's source, because this is a 10-step masterclass in shattering the illusion of the autonomous agent.
Walk us through it.
Step 1. You, the user, ask the front-end chat program for the weather in Tokyo. The program receives that string of text.
Right, the Python program in the backend.
Step 2. The Python program tells the LLM, hey, you have a weather tool. It injects a JSON schema into the system prompt that basically says, there is a function called getWeather. It needs a city name.
And it sends that whole bundle to the LLM.
Step 3. The LLM receives the payload, processes the tokens, and realizes you want the weather. So it starts predicting tokens, but not English tokens, JSON tokens.
Because it's been fine-tuned on code execution.
Exactly. So it outputs bracket, tool, getWeather, arg is city Tokyo, close bracket, pure JSON text.
And this is step 4, the LLM's job, stops. It just generates a stop token and terminates the connection.
It goes to sleep. It did no walking.
None at all.
Step 5. The dumb Python program reads that JSON string. It extracts the word Tokyo.
Right.
Step 6. The program, not the AI, constructs an HTTP request, adds the API keys, and calls the actual weather API.
The program does the walking.
Yes. Step 7. The weather API returns a response to the program. Cloudy, 18 degrees Celsius.
Step 8. The program takes that raw data, builds a brand new prompt, appends it to the chat history, and feeds this new text back to the LLM.
Step 9. The LLM wakes up from a blank slate, rereads the entire context desk, sees the new weather data injected by the program, and finally outputs human text. It's currently cloudy in Tokyo and 18 degrees.
And step 10. The program renders that text on your screen.
LLM talks, program walks.
Yeah.
The LLM is just the brain saying, I want this JSON thing to happen, and the dumb traditional software is the hands and feet that actually go out and do it.
When you abstract this out, the neural network is functioning solely as a highly advanced text parser. It sits in the middle of a traditional software stack, just acting as an interpreter between natural language and deterministic code execution.
Okay, but this introduces a really practical challenge, layer 5, giving the program a map. Because if the program does the walking, how does it know where to walk?
That's the fragmentation problem.
Right. If you're building this in an enterprise, you don't just have a weather API. You have a new AI employee in a company with dozens of complex internal systems, HR databases, Jira, GitHub, Slack. And historically, there was no tool directory.
Developers were forced to write an incredible amount of glue code.
It was a nightmare.
Yeah, if you wanted your AI to check a Jira ticket, you had to write the specific JSON schema required by OpenAI. But then, if your boss says, hey, we're switching to Claude tomorrow, you had to rewrite all that logic because Anthropic formats their schemas differently.
You had to build the same tool 3 separate times for ChatGPT, Claude, and Gemini.
Exactly. And that structural friction is what drove the development of MCP, the Model Context Protocol.
Which is such a brilliant solution. I love the analogy from the text here. It's exactly like USB-C. Like,
Yes.
Remember 10 years ago, we used to have, 10 different proprietary chargers for all our devices? Your desk was just a rat's nest of cables.
And before MCP, your code base was a rat's nest of schema translators.
Right. But MCP is the universal cable for AI tools. It's a standardized directory.
It operates on a build once, run everywhere philosophy. An MCP server basically provides 2 things: a catalog of tools and the execution of those tools.
So you build an MCP server that securely wraps your internal Postgres database or whatever. It exposes the tools using a universal schema.
Right. It sits between the LLM and the program. So when the LLM outputs text saying it needs data, the MCP client routes that request to the server. The server runs the SQL query locally and sends the text back.
The LLM never touches the database.
Yep.
And the developer never has to rewrite the integration.
Exactly. Standardized plumbing.
Okay, so with MCP, it can seamlessly do one action. It can check the weather or check a database. But layer 6, what if a task requires multiple steps?
The agent.
Right, the buzzword of the year, putting it on autopilot. because checking the weather and then doing something about it requires planning. So what is an agent really?
Well, again, we have to demystify the intelligence here. When tech companies sell us an intelligent agent, it sounds like they're selling us a digital employee that can think and plan independently.
But applying our mechanical framework LLM talks, program walks, what is it actually?
It is just the function calling loop running on repeat. It's a while loop programmed in Python, wrapping a text predictor until a multi-step task is complete.
It's literally just a while loop.
It's literally a while loop.
Let's walk through the umbrella shop example from Harrison's breakdown because this blew my mind a little bit.
It's a great example of the React framework reasoning and acting.
Right. So you tell the agent, find me a nearby umbrella shop if it's currently raining. The LLM doesn't formulate a massive master plan up front, does it?
No, it operates strictly step-by-step within that while loop.
Okay, so iteration 1 of the loop. The LLM gets the prompt. It outputs a JSON command to execute a geolocation tool because it needs to know where it is.
Right. The program intercepts the JSON, walks out, gets your GPS coordinates, and feeds them back to the LLM.
Iteration 2. The LLM wakes up, sees the coordinates on its desk, and outputs a new JSON command to execute the weather API tool using those specific coordinates.
The program walks, checks the weather, sees it's raining, and feeds rainy back to the LLM.
Iteration 3. The LLM sees it's raining and knows it needs an umbrella shop. So it outputs a third JSON command to query a Maps API for shops near those coordinates.
The program walks, gets the addresses, returns them.
And then finally, iteration 4. The LLM looks at all the accumulated observations on its desk and it synthesizes the final human-readable answer. It is raining. Here are 3 shops near you.
Exactly. The program is just enforcing a strict loop. It just checks a condition. Did the LLM output a final answer, or did it output another tool call? As long as it's a tool call, the program keeps walking.
So wait, what does this all mean? When tech companies sell us intelligent agents like GitHub Copilot or Claude Code, they're really just selling us a while loop wrapped around a text predictor.
Yes. The program executing the steps has zero intelligence. The only intelligence in the entire system is the LLM sitting in the middle, analyzing the feedback on its desk, and probabilistically deciding which JSON string to output next.
That is a total paradigm shift. It's just a state machine.
A non-deterministic state machine, yes.
Which brings up a really scary business reality, layer 7, embedding institutional knowledge. Because if an agent is just a while loop left completely to its own devices, jumping from API to API, it might make mistakes.
It will definitely make mistakes.
Right. Or it might ignore company policy. Like, how do we force the statistical probability engine to follow our specific rigid enterprise rules every single time it runs a loop?
This is where we get into skills.
Another great marketing term.
Yeah. But mechanically, a skill is essentially a pre-written rulebook or a checklist. It's literally just a markdown file stored in a fixed location for the agent to consult.
So if I have a really strict deployment protocol for my engineering team, like run the tests, check the variables, ping Slack, wait for manager approval.
A skill is just a markdown file with that checklist.
Exactly. But here's the architectural problem. If a company has 1,000 standard operating procedures, you can't load 1,000 markdown files onto the LLM's desk at the start of the session.
Because of the token limit and the quadratic scaling costs we talked about?
Right. You'd bankrupt the API budget.
Yeah.
So you have to use a pattern called progressive disclosure.
Progressive disclosure.
Yes. It's a fundamental trade-off between token cost and information completeness. You operate in 3 levels. Level 1, you just scan the names and short descriptions of the skills.
Like giving the LLM a table of contents. Exactly. Very low token footprint.
Uh-huh.
Then, level 2. If the LLM decides it needs the deployment skill, it outputs a tool call to load it. The program fetches the full markdown file and opens that specific chapter, putting it on the desk.
Ah, so it only loads the full instructions when there's a match.
Right. And level 3. It only loads referenced scripts or deeply nested documentation when specifically needed to complete a step in that chapter, like checking a footnote.
I have to laugh at this realization, honestly. So a skill, this highly marketed enterprise AI feature, is just a fancy term for a system prompt that lives in a different folder until it's needed?
That's exactly what it is. It's dynamic context injection. You don't shove the whole library into the window up front.
Yeah.
You load just enough, optimally, to keep the agent on the rails without blowing up the compute costs.
Wow. Okay, let's look at the big picture here and reassemble this entire stack from bottom to top because I think we've completely deconstructed the magic trick.
Let's do it.
At the absolute bedrock, we have the token, the atomic unit of compressed math. Then we have the context window, the desk, the strict memory limit.
Then RG, the vector database that puts only the relevant pages on that desk.
Then the prompt, the hypervisor rules that dictate how the AI acts.
Then function calling, the generation of a JSON schema that bridges the gap between text and action.
Then MCP, the universal USB-C catalog of tools.
Then the agent, the programmatic while loop that repeats the process.
And finally, skills, the Markdown rulebooks progressively loaded to keep the loop safe.
And the ultimate takeaway here, the thing you have to internalize, is that none of those actions belong to the LLM.
None of them.
The LLM's sole contribution to the entire AI ecosystem is outputting the right text at the right time. That's it.
LLM talks, program walks.
Exactly.
So as Harrison points out in his toolkit for operators, the next time a fancy new buzzword drops like, I don't know, agentic RAG or orchestration framework, you don't need to be intimidated. Just ask two simple engineering questions.
Number one, what text did the LLM actually output?
And number two, who read that text and turned it into an action? Because it wasn't the LLM.
It's always the surrounding software.
Always. And as we wrap up this deep dive, that leaves me with a really provocative thought, something that wasn't explicitly in Harrison's text, but builds directly on this whole architecture.
What's up?
Think about it. If the LLM is just a talker, permanently constrained to outputting text, and the surrounding program is the dumb walker that actually executes actions in the real world.
Right.
At what point does the speed and the complexity of the program's walk outpace our human ability to monitor what the LLM is actually talking about?
Oh, that's the real danger.
Exactly. When the universal USB-C of AI plugs directly into our bank accounts, our server infrastructures, our physical power grids,
Right.
the bottleneck isn't the AI's intelligence.
No, the AI is just guessing the next token.
The bottleneck is the guardrails we code into the dumb program. If the LLM hallucinates a JSON string that says delete all database tables, and the dumb Python program just blindly parses it and executes the SQL command, that isn't a failure of artificial intelligence. It's a catastrophic failure of traditional software engineering.
The execution layer is where the risk lives.
Precisely. The most vital code you write moving forward won't be the prompt. It will be the try-catch block wrapping the execution.
Absolutely.
Thank you for joining us on this deep dive. As the landscape continues to shift and the hype gets louder, remember to ignore the packaging, inspect the plumbing, and keep asking, who is doing the walking? We'll catch you next time.